Dear science lovers, welcome to Jawaharlal Nehru Planetarium, Bengaluru. As you know, Jawaharlal Nehru Planetarium is organizing many programs. Maybe it is an academic, non-formal academic programs or the science popularization program. We have many flagship programs. For example, the weekend course that we conduct, which is called as a REAP, Research Education and Advancement Program. It's very popular among the undergraduate students, which actually introduces them to the research career or research eternity. So there are many flagship programs. In coming to the science popularization program, we have many programs, like one of the very much people gathering program, or people which attracts many people, is this one, which is all of you know that it's a Coffee with Curiosity that we organize in collaboration with ICTS. So here today we have one of the a very much interested talk for everybody, every one of us. So as we know, today, this week, it was on the occasion of World Space Week. We conducted many programs here to bring awareness about the space activities and the space programs that have been conducted from when the Sputnik was launched and all the space programs after that. So many people attended the programs, like the walk-in quiz that we conducted, and also we conducted a Aditya model making for school students, which attracted many school students. So it was introduced. It was to introduce the objectives of the Aditya L1 mission, which will be studying the moon. Which will be studying the sun, right? So many such programs were conducted in these 3 days. So please, for more information about the activities that the planetarium conducts, please visit us on www.taralaya.org. Maybe many of the programs is also of interest to you. Now I request Professor Ajit to introduce the speaker.
Good afternoon. It's a great pleasure to welcome all of you to today's KAAPI with Curiosity lecture, and to introduce today's speaker, Professor Nils Andersson, who is at the University of Southampton in the UK. He is a world-leading expert on neutron stars and gravitational waves. Apart from his very important and seminal contribution to the study of neutron stars, he has been extremely active in training the next generation of scientists. He has written a very important textbook on neutron stars and gravitational waves, and several popular books. He's very extremely passionate about communicating science to the public. In fact, he and his collaborators were so kind to give us many copies of his very interesting popular book called A Gentle Wizard about Einstein. And if you would like, you are welcome to pick up a copy of that book for free from the counter here. And apart from this very interesting book on Einstein, he has written, you could see that he combines humor with science, and he has written this very interesting series of books called Professor Compressor, which explains very interesting aspects of science and technology to young readers. And if you are interested, you are welcome to pick up these books from Amazon, not here. His talent is really multidisciplinary, multifaceted. Apart from writing and communicating science, he also has worked with artists to bring out very interesting concepts of science in the form of books and other forms of communicating science. And we at the Indian community has been particularly helped by him in producing an interesting book that describes gravitational waves. And this was translated to several Indian languages and was circulated to school children in Maharashtra in particular, where the new project LIGO India is coming up. That will be a next detector that will be going after the detection of gravitational waves. So with a few of these words, let me welcome today's speaker. And let me also ask my colleague, Professor Payush Kumar, to hand over a memento to Professor Andersson as a sign of our love and our welcome.
Wow. Wow, look at that. You know, you give the presents after, otherwise I can just run now, right? Got the loot, I can just go. Thank you.
Let me also add that Professor Andersson is a very long associate and collaborator of Professor C.V. Vishweshwara, the founder of this planetarium. So it's particularly heartening to see him speaking at the planetarium. So we're particularly glad that he is here in the planetarium speaking to us.
Okay. Yeah, shall I help you switch it off? All right. Thank you all for coming. It's great to be here. I actually visited this planetarium in 1995, I believe. Don't look at me like that. I know some of you were not born then, but you know, some of us are much, much older than we look, and we look old. So that's the way it is. Okay. Secondly, I'm going to apologize a little bit for my voice. There's a medical thing going on, and it is what it is. I'm going to try to survive for about an hour, and that's it. And then I'll just go for a lie down, like old men should. Okay, so this talk, I'm sorry to scare you a little, but this talk is a matter of life and death, okay? Hopefully, everyone in the room will be okay. The stars will not. So as you know, I'm sure, stars, just like people, live and die. But the difference with people is that stars can have a more interesting afterlife. I mean, depending on what you believe, of course. So in the case of our sun will age a little bit like an old man, right? It will get fatter and fatter, and then eventually fade away and form a white dwarf star. I'm not going to talk about white dwarf stars because I find them a little bit uninteresting. I'm sorry to the science community. It's a hard thing to do, but what I'm going to do is talk about things that are much more exciting than that. So white dwarfs are exciting, but we're going to ramp that excitement up a little bit, okay? So what happens when a bigger star, weighing maybe something like 8-10 times as much as the sun, runs out of fuel, stops burning to create heavier and heavier materials? Well, it typically can't hold itself up. Gravity takes over, the star starts falling in, and it explodes in a supernova explosion. And the question for today is, what's left over? A normal star has died, what comes after? So what happens when you die and you rise again is a zombie, right? And there is the title of the talk. So I'm going to talk about the stars that may form when normal stars die. So they're not white dwarfs, they're not black holes, which we will come to in a minute. They're in between, we call them neutron stars, and that's the topic of today's talk. Okay? So the motivation for what I'm going to talk about comes from, I think in a sense, this quote from Arthur Eddington, who you probably recognize as the man that led one of the expeditions to measure the gravitational light bending, setting Albert Einstein on the route to fame in 1919. So the way Eddington put it is that you calculate, so you sit with your little theory and your booklet, and you calculate according to the laws of physics that you understand, or as you understand them, and then you go to your friendly astronomer, if there is such a thing, and you ask them, okay, I've calculated this. Does this remind you of anything that happens in the sky? Okay? If the answer is yes, you go and win a Nobel Prize. If the answer is no, you go back and calculate again. Okay? So here's a very famous man that calculated and that knew a fair bit about the laws of physics, probably more than most of us. So Chandrasekhar, who as a young student on the way to England to do his studies at Cambridge, famously worked out that if you combine gravity and quantum theory, a white dwarf star that I mentioned earlier, cannot be heavier than a certain amount. So you can have white dwarf stars, but they can't be heavier than some number, a little bit heavier than the sun, okay? And that led to a bit of a conundrum because in Albert Einstein's theory, we learn that gravity can overcome everything and basically create what we call black holes. Thank you.
Can you speak a bit louder?
I can try to speak a bit louder, that's okay. But in the 1920s, nobody understood black holes. And in the people that thought they did, thought they couldn't possibly exist. Okay? So with Chandra's calculation, we learned that white dwarf stars cannot be heavier than a certain number. Something else has to happen, but black holes we didn't understand, so there was a mystery. Okay? So what happens is, if you imagine a star collapsing in on itself, it gets denser and denser. So the particles get atoms get closer and closer, until they start pushing each other, until they start pushing through each other, until you just get the constituents that make up the atoms. So what makes up the atoms? Well, first, in the first sort of thing that stops you is neutrons, protons, and electrons. Okay? That's how we build atoms. And so the neutrons, protons, and electrons are going to be the starting point for this story. They're the building blocks. We need to ask, what happens if we take a ball, a star, it collapses in, we just keep on pushing with godlike power, we push in and push in and push in until these neutrons, protons, and electrons start talking to each other very closely and they get uncomfortable because they're a bit too close to each other. Okay? What happens? What do the laws of physics do? And how do we calculate to follow Arthur Eddington to predict what happens? Okay? Now, I put these three gentlemen on the slide because you may know that the electron was discovered by Thomson in the 1890s, late 1890s. The proton was discovered by Rutherford a little bit later, some 20 years later. And finally, Chadwick discovered the neutron in the 1930s. What you probably don't know is that Thomson was the PhD supervisor of Rutherford, and Rutherford was the PhD supervisor of Chadwick. So this is very much a family affair, the nuclear family, if you want. Okay? Now, they all won the Nobel Prize, not surprising because these were all breakthroughs, helping us understand basically how atoms work. Right? And they're clearly the fathers of nuclear physics with all the good and bad that this brings. Now, you may not be surprised, because you know that scientists are creative and sometimes a little bit crazy, to learn that the moment Chadwick discovered the neutron, people started suggesting that, well, why don't we build stars out of these things? Why don't we build neutron stars in the 1930s? Okay? So the neutron had been discovered. Someone thought, I can calculate. So they calculated and said, look, I can build a star out of this. Let's call it a neutron star. Okay? So now you go to your friendly astronomer, and they can do nothing about it because neutron stars, if they exist, would be tiny. They would weigh the same sort of level as the sun, but they would maybe just be 10, 20 kilometers in radius, and you have to have a rather good telescope to see such a thing. Basically, you can't, right? So that's the problem. They're heavy but small. Astronomers are no use to you. Although a different kind of astronomy comes in to help you, in this case, in the first instance, radio astronomy. So the story goes, as you probably know, that in the 1960s, late 1967, Jocelyn Bell Burnell, a graduate student at Cambridge, was working with data from their new radio telescope when she found regular blips, like a beat and then a beat and a beat. And they thought, what could this be? We've never seen anything like this. The first thing was, this is wrong. So they checked the instrument and all these things. It seemed to be fine. The second one was, it's man-made. There's something going on next door, you know. The next door neighbor is cooking or whatever they're doing. No. Finally, there was an idea, maybe a joke, that these were signals from extraterrestrials. So the first radio pulsars, as we now know them, were labeled LMG, for little green men. That didn't last very long, because a few years later, it was established that these were rotating neutron stars which we see because they have strong magnetic fields. And as the magnetic field spins around, it's like rotating a bar magnet. You're going to emit electromagnetic radiation, preferably in directions along that rotation axis. So I've got an illustration of the magnetic field. Here are these big lobes. The star spins like this, but the magnetic field is misaligned a little bit. So you get these emission in cones, effectively. And every time this cone sweeps past your telescope, you see a signal, right? So that's the birth of radio pulsar astronomy. Today we've seen about 2,500 such objects. Some of them are monitored more or less daily, and we've learned a lot about neutron stars this way. But I'm going to not talk very much about radio astronomy until towards the very end. So let's go back to the theory, the physics. How does it work? What happens if I take this ball of neutrons, protons and electrons, as it turns out, and squeeze it? Well, let's just get a picture of what we need to do, okay? So this comes from Neil deGrasse Tyson, and it's a measure. You can calculate what the density would have to be of a neutron star many different ways. I like this one because it has elephants in it, and everyone knows that elephants just rule, okay? So he worked out that you take a herd of about 50 million elephants and put them into a little volume like that. Then you would they wouldn't be comfortable, they wouldn't like it, okay? You'd probably end up in trouble if you tried. That would be the density, so the mass per volume that you need to build a neutron star out of elephants. Now, no one is suggesting we do this, but you know, certainly we'd run into trouble with all the animal welfare and all that stuff. But you know, if Ajit can source 50 million elephants, I'm willing to give it a go. Okay, so this is my version of what the neutron star looks like. Don't worry about it too much, it's just a sketch. But I just want to talk you through it a little bit and then talk about what the ingredients are. I have some small writing that you can't see, don't worry about it. Basically what happens is, you start at the surface, right? Where you have something that's roughly the density of iron. So you can think of just normal iron, which we understand, right? Then you get more dense and more dense, at which point you build more and more what we call neutron rich, so heavier and heavier atoms, until at some point the neutrons don't like the protons and electrons anymore, so they start leaving the atoms and forming a gas that exists together with these atoms. You go a bit further with these atoms, and then suddenly the protons decide that they actually don't like these atoms either, so they become unstable and leave the atoms, and suddenly you have a gas of neutrons, protons, and electrons that we talked about earlier, okay? Which we can try to understand because we understand the nuclear physics in some sense, just not at these densities, okay? And then you can keep on pushing, because why not, while you're at it. At some point, you're going to squeeze so hard that the neutrons start touching each other, at which point you have to ask, what are the neutrons made of? And they're made out of quarks, right? So if you push hard enough, the quarks might decide that they don't like to be inside the neutrons anymore, and suddenly you have a quark-gluon plasma, so basically a gas of quarks. Now we think that that is very likely to happen in neutron stars, and one big research area today is to try to figure out if that is true, that this does happen, how can we tell? What are the signatures in observations that will tell us that this actually did happen? And that's debated. Okay? So this diagram is a little bit too messy, I know, but I think it's colorful, so I wanted to use it. So let's do a different game. Let's ask, what piece of theory, what kind of physics do we need to know to do the calculations, okay? So I want to do Eddington's calculation. What do I need to know? So first of all, you need to understand the four, I always put out the wrong number of fingers, because it's four, okay? The four fundamental forces. We need gravity, right? Because gravity is what holds the star together. It doesn't fly apart. Gravity will also, in a moment, give us gravitational waves and all sorts of fantastic things. So, in essence, you need to understand Einstein's theory of gravity, general relativity. If you know anything about physics, you know that, okay, you're in for a treat, but you also have to work hard. We need to understand electromagnetism because these guys, as I said already, are rotating magnets. In fact, they have they're probably the strongest magnets in the universe. So with field strengths, there are, I think, some more than 10 orders of magnitude stronger than the sun and things like that. Okay? Everything else is puny. Neutron stars are super magnetic. We need to understand what they're made of. So nuclear physics tells us that you can't just have a ball of neutrons. You have to have some protons and some electrons thrown in. So we need all of those three guys from that slide. But the question is, how many protons do you need? And how many electrons per neutron? The answer to that comes from something called a strong interaction. That's how nuclear physics works. It's basically the strong interaction. And then we need to understand how the star ages, how it gets cooler, how it grows old with some dignity or not. And that's the weak interaction, which is also a nuclear physics thing that involves a pesky thing called neutrinos that you may have heard of. In fact, Ajit told me a story about neutrino telescopes on the way here, which I will not repeat. It was not suitable for any audience, because you might run for it if I did. It includes the word radiation, and everyone knows that as soon as you say radiation, people go, oh, sorry, no, not touching that. So we need the four fundamental forces. Okay, now we think we understand the four fundamental forces, but unfortunately that's not enough. We need to build a star, so we need to worry about what is the state of matter. Okay? Now you probably all know that the ancient philosophers distinguished between, again, four elements, right? We had earth, air, water, and fire. Okay? So modern physics is very much the same, right? We have earth, we have solids, we have water, we have liquids, we have fire, we have basically plasmas, and we have air, which is gas. Okay? So how does this work? Well, in a neutron star, it turns out that the outer layers, because a neutron star is kind of cold, but it's kind of hot. So it's kind of hot because it's something like, mature neutron star is at the temperature of maybe 100 million Kelvin. Okay? You think that's hot. Nuclear physics thinks that's really cold, because nuclear physics thinks that a million Kelvin is kind of normal temperature. So this is really cold. So when matter is cold, what does it do? Well, we know water, it freezes, right, to ice. So nuclear physics says the same. So neutron star matter freezes to form something we call the crust. And that is about 1 kilometer at the outer edges of the star. Below that, we have a liquid. Basically, at first, neutrons, protons, and electrons in a liquid form. And also there might be a little, really tiny, maybe millimeters, maybe meters, thick ocean of basically dissolved iron at the very surface. And then outside that there's gas, there's an atmosphere. So far everything is normal. What happens if you take atoms and squeeze them? Well, if you squeeze hard enough, they're going to start breaking out, as I said, into ions and electrons, a plasma. That happens in neutron stars too. As I said, the neutrons squeeze out of the atoms and becomes ionized. So we have an ion, gas, or liquid combined with electrons. And also outside the star, we've got an electron-positron plasma. So you have plasmas. But we can do better. If you go to the deep core, where you have these quarks, and you cool that down, that is a quark-gluon plasma. If you cool that down, it could form something called a color superconductor, which I didn't even dare put on the slide, but I can say it in words, hoping that no one pays attention. So there's not 7, there's now 8 states of matter, so I messed up, okay? But this brings me to the next thing. If you cool neutrons down, or anything, if you cool helium down, it becomes what we call superfluid. It can flow without friction. A neutron star has a superfluid because the neutrons are neutral, they can become superfluid. Okay? Protons and electrons are charged, they don't become superfluid, they become superconducting. Okay? I already mentioned superconductors. And now I think your heads are spinning. There are 4 fundamental forces, at least 7 states of matter. Your task for the rest of this presentation is to go away and calculate and make sense of this. You may appreciate this is not easy. I think there's no one on the planet, I'm probably insulting some of my colleagues, I don't mean to, but certainly I don't know how to do this, okay? I know how to do some of these bits, but not all of them. In fact, I often joke that there's this famous series of textbooks that was popular in some sense, or unpopular because the students had to read them, in the 60s, 1960s, written by Lev Landau and his colleagues Lifshitz and Pitaevsky after that. They span all of physics. And I often say to students that the first thing you do is you buy these books and you read all of them and then you come back and talk to me. And I never see these students again. So basically, this is all of modern physics. Neutron stars represent everything. Well, give or take a few things that it doesn't do, like cosmology, but okay, look, I'm not making, it's the ground statement, but it's not far from the truth. You can be a cold matter, low temperature physicist and work on neutron stars. You can be a high temperature plasma guy and work on neutron stars. You can be a nuclear physicist, QCD expert, high energy physicist, fluid dynamics person, you know, and you can even be an astronomer, okay? So this is pretty much all of physics, which is why I like neutron stars. In fact, I love them because I don't understand them. And if you want to do science, you know that what you really want to do is have an opportunity to keep on learning, okay? And the best thing ever is if you never run out, right? There's always going to be a problem that's a little bit harder than the previous one. And here is your problem. Okay. So in terms of observations and experiments, one way of thinking of neutron stars is in terms of this phase diagram, temperature versus, it says chemical potential. When it says chemical potential, you read density, okay? So it's just bad spelling for density. So what we do with experiments in nuclear physics, particle physics, we build colliders, right, and crash things together. Now, these colliders, like the LHC at CERN, for example, Rick at Brookhaven, measure collisions that create matter that's very, very hot, but not very dense. So basically in this diagram, you sit at high temperatures, but low densities. So up at the top left, okay? Neutron stars are cold, as I said, but very dense. So they actually sit on the opposite axis, far at the bottom right. And that means that when we're trying to do these calculations, experiments from the Large Hadron Collider and so on, which teach us all sorts of wonderful things about particles, are pretty useless, because I don't know how to extrapolate the results into that other corner, okay? So that's difficult, but it's an opportunity. It just means that astronomy suddenly is contributing to our understanding of high energy physics, which is good for us, because that means people are interested in the calculations we're trying to do. Okay, so this is kind of what we know and illustrates a little bit what we don't know. This is a plot of the mass of neutron stars, so how heavy they can get. And if you remember that story about Chandrasekhar calculating the maximum mass for white dwarfs, there's also maximum mass stars, which we think is just about twice the mass of the sun, okay? And you can see all these thin curves sort of flatten out and reach a peak. That's that mass for some particular model, okay? And then against this, I'm plotting the radius, so you can see that for a typical neutron star, the radius is about 10 kilometers. So they're small, as I said. And then what you have on this is some observed radio pulsars, right? With the bands that go across. The thin blue is the record holder in terms of mass. That's the heaviest neutron star we have, okay? Now, what do we learn from that? Well, we learn that in nature, we have to be able to build a neutron star at least as heavy as that, right? Because it exists. And if the theory says it doesn't, then the theory is wrong. And so you can see here, for example, here's a curve that doesn't reach up to this. So this curve is a theory that's wrong. And there are a few of those I put on here. So these curves are different theory models for how neutron stars work. And you can see quite a few of them don't reach up to that height. So they're wrong. But of course, the people that calculated these things are clever, so they go and calculate again, and then that curve suddenly reaches that point it has to reach, because that's what the theory has to do. So that's what the theory will do. Now, then there are some curves, as I said, they span the range basically of our ignorance. And then there's a band, which I've colored in, which is basically a region that we think, based on our best understanding of the theory, how quantum theory works, where neutron stars should sit. And again, you can see there are some curves out here, some curves over there that don't quite fit, okay? So maybe we can rule those out. But you can also see there's a bunch of curves that are totally fine in the middle, all of them kind of vanilla in this measurement. We can't tell the difference, okay? We'd like to, but yet we can't. So this is the challenge. Okay, now, I'm going to change direction. I could choose to talk about all sorts of different observations of neutron stars, but I'm going to focus on one particular direction, because I want to focus on gravity. So I'm going to talk about gravitational waves a little bit. So, if you've seen these talks before, if you know anything about this, you know that Albert Einstein's theory of gravity, general relativity, predicts that massive bodies can generate gravitational waves. In fact, as soon as any body accelerates, there will be some gravitational waves. But the problem is gravity is really tiny as a force. So gravitational waves are really weak. So they're difficult to catch, difficult to create. Okay? But we've known since the 1970s, thanks to neutron stars and radio astronomy coming back to play a role, that these gravitational waves are probably real. Because people, detected or discovered a double neutron star system, two stars going around each other like this. As they go around each other, they generate gravitational waves that leave the system. As you lose energy because you radiate waves, the stars get a little bit closer together. You can calculate that in Einstein's theory, and people did. And they found, after tracking, you can see if you can read this down here, from 74 for 30 years, they tracked, the dots are the data, and the general relativity calculation is the line. So you calculate according to the laws of physics, general relativity, go to the astronomer friend, they measures, and you check, and it works. Gravitational waves are needed to explain this system called the binary pulsar. The discoverers won the Nobel Prize. No surprise. Now, you can ask the following question. We have this double neutron star system. It's losing energy. The stars get closer and closer together. If we run this forward a million, a billion years, something like that, what's going to happen? The two stars will have to crash together, right? What happens when they crash together? Well, we're going to create something, well, a real mayhem. We're going to create a sort of cosmic collider experiment, right? And so this is going to be the Large Hadron Collider on absolute speed. So the question then is, this binary pulsar thing was an indirect statement. We don't detect the gravitational waves, can we? So that was the motivation for building the LIGO experiment starting in the 90s. And as you probably know, because you've got experts at ICTS that talk about this, I'm sure, all the time, you know, we all need to validate our existence, so that's what they do. You have some really excellent partners in the LIGO experiment in India, so you should pay attention to them. So as you probably know, LIGO detected the first gravitational waves from two black holes, which I haven't talked about, but they're basically really boring. Actually, they're really fascinating, but there's no real physics other than gravity, which is good, because it makes them easy, but they're not as fascinating as neutron stars, at least not this afternoon. Okay? So LIGO detected the first binary black hole signal in 2015, and by now, they've seen so many that no one bothers to count anymore, 100, okay, give or take. And the experiment is running now, collecting more and more data, although there are some problems with that, but let's not talk about that. So what is the LIGO experiment? It basically measures how space and time stretches and squeezes as gravitational waves pass through. That's all you're going to hear about this for now. But because if I start talking about that, that's going to be some other talk. So I want to show you a movie. And I want to show you this movie because, well, frankly, it amuses me. And so that's not bad. But this is a movie from a numerical simulation of two neutron stars crashing together. There's nothing special about this movie, I have to tell you. There's tons of people in the world can do this. There's nothing special. This happens to be my group. There's only one thing about it that you will not get from anybody else. I'm going to give you the sound, okay? But before I show you this, there's a story to go with this. So we had the student that did this, ran the simulation, and then as a joke, which tells you never joke with your students, I said to him, that's all fine, but you know, the LIGO guys, when they show the black holes, they play the sound, because it happens that the gravitational waves are in the audible range. So you can do this, just put it on. And I thought, why nobody ever does this for neutron stars. Can you not give me the sound? Okay, and then I traveled to a conference, right? And I was at the conference dinner, and a ping said my phone for an email, and he'd sent me this video, not exactly this, but this kind of video with the sound, which I'd never seen before. And I thought it was the funniest thing. I'm a scientist, remember, so when something is funny to me, it might not be funny to you. But I thought it was the funniest thing ever. So I showed it to people at this dinner. I said, look what we did, it's fantastic. And they said, yeah. Okay. But then, last summer, I was at Aspen at the physics meeting. And a lady colleague came up to me and said, you remember that movie? I said, what? What are you talking about? Oh, that movie with the sound. I said, yeah, I remember. But I think I've lost it or something. I said, and she said, can I have it? I said, why do you want it? And she said, oh, I want it for a NASA press release on our work. And I said, okay, now we're in business. So this was a joke, but this is actually, now this movie is the new version, which is the NASA version. Okay. So I'm going to play you this, and I'll tell you what's going to happen. First, you're going to hear the gravitational wave signal increasing in frequency and amplitude as the stars, you've seen this before, because everyone shows this for black holes, right? Then, you're going to see the stars crashing together. Pay attention to what's happening then, because that's the thing I think is funny. Okay? Okay? Okay, so it starts like this. And it gets really loud, so maybe not, okay? But, okay, it's going to get really loud. But it's so boring. It's so incredibly boring. So I'm going to fast forward a bit, okay? Because for some reason, NASA wanted several minutes of this nonsense. Okay, we're going to go here. Okay, now we're getting closer. You hear the frequency is higher. Now, wait for it. It's going to be so disappointing. Okay, I can stop it there. If these were two black holes, you wouldn't hear that crazy bird, okay? That crazy bird is at the end when the two stars come together, you form a new star that lives for a little while, okay? Now, that part of the signal we haven't seen yet. That's one of the big challenges for future gravitational wave astronomy, is to catch neutron stars imitating crazy birds. You might understand why I liked that. First time I saw that, I thought, that doesn't make any sense. Oh, not that again. Okay. Okay, so, but we have seen, neutron stars merge. So here is the time frequency plot of the first neutron star binary in spiral detected by LIGO in August 2017, followed by, a couple of seconds later, a flash from the Fermi satellite indicating that there was a gamma ray burst emitted after the two stars came together. And there you have it, an artist's impression of what that jet emission could look like, followed by a cocoon of matter being thrown out. And as it moves out, it undergoes rapid nuclear reactions to build very heavy elements. Okay? It's called a kilonova. And so this event, what we call 1708-17, is incredibly famous, at least in astronomy, at least in gravitational wave astronomy, at least among people that worked on it or something like that. It's very famous because it was the first neutron star binary gravitational wave detection. It was a demonstration that these events generate what we call short gamma ray bursts, something people had speculated but never proved. Okay? This is evidence. And it was the first solid detection of this kilonova emission following. So it does several firsts for astronomy, which is amazing. And I think L in LIGO stands for lucky, because the first binary black hole detection actually happened before they officially started taking data. A spectacularly strong event when they were just tinkering around with the machines, getting ready. This is a very nearby event of something that's actually quite rare. So I think it's the lucky interferometric gravitational wave observatory. That's what I think. Okay, and then I'm just showing it doesn't matter how all the different branches of astronomy, from X-ray to gamma ray to optical, even backyard amateur astronomers observed this event. So this is, I think it's something like a third of the world's astronomers took part, which is quite amazing. Okay, so we're talking about neutron stars. What did we learn about neutron stars from this? Well, actually, not as much as we would like. Because the problem is, we didn't catch that crazy bird. We didn't catch the merger itself. We only catch that early part of the signal, where the only thing we can see is some very faint imprint of how one star stretches the other, like races a tide on it, because they're fluid bodies. And that allows us to say something about what the star is made of, not very much, but we can say something about the radius. And here is a kind of constraint that comes out from this, on top of that plot from before. So we get some error bars. It's not very precise. It's drawn by hand. Just don't want to get too confrontational with whatever other people think this should be. But you can see I'm beginning to squeeze into this pink band, but frankly, not very much. Okay? So in the future, we're hoping to do this much better. But that means we need to understand the tidal interaction and what that does to neutron stars. And that's a difficult problem. And then finally, the thing that the press had a field day with, from the kilonova emission, we've learned that the amount of heavy elements, platinum and gold in particular, that's thrown out from this is enough to explain all the heavy elements on Earth. All the gold comes from neutron stars crashing together, plausibly. And I think that's quite amazing, because it means that if you have a gold ring on your finger, it means you're carrying around the remnant of two dead stars, two zombies, that crashed together perhaps millions, billions of years ago in a distant galaxy. I think that's hard to compute, right? Okay, so I'm going to wrap up a little bit in a few minutes, but let's just do the obligatory. There was, no surprise, a Nobel Prize for gravitational waves to Ray Weiss, Barry Barish and Kip Thorne, not entirely unknown scientists, I suppose. Especially Kip, who's written fabulous books on physics. He has a tradition of writing textbooks for those of us who are experts that we can't lift, because we don't go to the gym often enough. Books like that, okay? I like to write little books like this. He likes big books. And Ray Weiss on the left, who invented effectively what became the LIGO experiment. So the theory and experiment working together, which I like. So I'm going to finish by talking about radio pulsars again, because it turns out that not only can you detect the pulses and learn something about neutron stars that way, you can also use the pulsars to detect gravitational waves. And the idea is this. With a pulsar, you've got a very, very precise clock that spins around and loses energy very, very slowly. Okay? You measure the ticks, you can see how it spins down. But many of these objects slow down very, very slowly, meaning they're very, very stable clock. They're actually as good as some of the best atomic clocks that we can build, even though they're 10-kilometer objects whizzing around maybe 1,000 times a second, okay? Which is crazy. But these signals have to travel to us on Earth, which means they have to traverse space in between where they are and us. And then you can imagine a gravitational wave, but a really long gravitational wave, right? Stretching and squeezing space in between us and the pulsar. That should leave an imprint on this signal. And now you can imagine that I've got many of these, hundreds maybe, or at least a couple of dozen, and I keep track of these, and I ask myself, is it possible that there could be a big gravitational wave going through space, and it's present in these signals? If that were so, these signals would have to, a variation in these signals would have to be correlated. They have to depend on each other. And you can calculate, again, like Eddington told us, what this should be, okay? People did. There's a curve. This is the only real scientific diagram I have, because I couldn't come up with a funny way of doing this. I was working on it, okay? It's called a Downs curve. It looks like this. And so here I'm showing a subset of data from what are called pulsar timing arrays. There's an Indian pulsar timing array that contributed to this, so you can be proud of that as well. And now if you look at this, what you want is the data to match that dashed curve. It doesn't matter what it is, you can all see that kind of tracks that or not. You can also see you have to squint a little bit to convince yourself that yes, it does follow that curve, okay? So it's not super convincing, but it is beginning to get there. And the idea is that the results we've seen in this year, published now, recently, are from the individual collaborations. When they put that data together, we think this is going to be convincing, a real detection of gravitational waves. But the gravitational waves I talked about, the stars crashing together, are in the audible range, 100 hertz. These guys are in the nanohertz regime, right? So this is so slow that you can't even imagine how slow it is. Okay? And basically, those gravitational waves have to come from when the universe was born, or something like that, really big black holes crashing together, maybe weighing as much as 1 billion times as much, oh, 1 million times as much as the sun, that sort of thing, right? So this is something to pay attention to, and something very recent, saying that gravity and gravitational waves, neutron stars, continue to be in the news. It continues to be exciting. So what happens next? Well, what's going to come next is we're trying to get money, because frankly, we're all a little bit greedy. We're trying to get money to build the next LIGO. Something better, something bigger. Not necessarily more beautiful, but something bigger. So we call this next generation. This is something that will start operating perhaps in the mid-2030s. There are two proposals out there being discussed. In the US, we talk about the Cosmic Explorer. In Europe, we talk about the Einstein telescope. They're similar in some sense, different. I'm not going to talk what they are. But what I'm showing here are two things. First, there's a little plot here showing what these guys are going to do. And you only have to look at the outer layers. We hope to do cosmology, to learn about the universe. We hope to understand black holes. We hope to understand gravity, and we hope to understand neutron stars, dense matter. So there's motivation for this kind of work going into the next 10, 15 years easily. And then someone just has to give us a small matter of $2 billion to build an instrument like this. But surely, if you all take out the money you've got, sorry, that's not going to. This is the kind of experiment that we need to balance the Large Hadron Collider. And this is going to be something that will have to run for decades, okay? But what's it going to do? Well, the other plot says, what could you see? And it turns out you can see all the black holes of sort of 10 times the mass of the sun that ever formed in the universe, going back to the formation of the very first stars. Okay? We will see all of them if they merge. Okay? This is crazy. If you imagine going back, looking at events that happened some 10, 12 billion years ago, everything throughout the universe. So I think that's one of the biggest ideas in gravity you can imagine, which is maybe why it's so expensive. And then, of course, hopefully before 2035, we have LIGO India. And I think if they build it to look like this artist's impression, I expect it's going to be a tourist resort and not a science experiment. But with that, I'm going to close. Thank you very much. I'm very happy to take questions.
Thank you, Nils, for taking us through this wonderful trip to this interesting life of zombie stars. So we are open for questions. If you have a question, please raise your hand. One of our volunteers, Anupam Ghosh, will bring a mic to you again.
Good afternoon, sir. My question is, what happens if the neutron star hit back the black hole?
Aha, excellent, thank you. Okay, so there are two options. One is really boring. One option is that the black hole is big and the neutron star is little, in which case the only thing that happens is the neutron stars go straight in. Nothing exciting at all. If the black hole is small, relatively small, then the first thing that happens is it starts raising tides on this neutron star, and the tide gets so strong that the star is ripped apart. Okay? And then it basically just forms a disk of matter that eventually falls in. Now, with gravitational wave observations, we should be able to tell the difference. But not yet, because we need to be able to track those last stages that we can't see yet with LIGO. We need an instrument like, probably something like a cosmic explorer to do this. So that's a really good question. It's a difficult problem. All problems are difficult. But we kind of know what's going to happen. We just don't know exactly, how the physics decides to detail the fine print, if you like. That's something people are working on.
Yeah. Sorry. Sir, I have two questions. One is, neutrons are basically neutral.
Yes.
A neutron star, okay, in 1967, it was actually its existence was known. Jocelyn Bell, Bernard, you mentioned. See, through radio waves, when they intersect with the direction of the Earth, they were detected. So neutrons, since they are not charged particles only emit magnetic field. Which part? Yeah, of course, you very nicely explained how the cross section of the neutron star. Which part of the neutron star, from the core to the crust, contributes to the radio waves generation? That is my first question. My second question is, are all neutron stars pulsars or not?
Oh.
Thank you.
So the second question, I'm 99.999% sure that the answer is yes. Because what else? Okay, so I cannot think of anything else other than a neutron star that can give you that stability and that compactness. So that I'm pretty sure about. The first question is basically, he's asking, how do radio pulsars work? Okay, I'm going to disappoint him because I don't know. But unfortunately, nobody else really knows either. One of the big problems in radio pulsar astronomy is to explain where that how that radio pulsar mechanism works. There are theories, don't get me wrong, there are as many theories as there are scientists, right? But none of the theories exactly does the job, okay? And this is, if you're interested in electromagnetic astronomy, is a real big question. Now, why is it difficult? Well, it's difficult because we're talking about really strong magnetic fields and so on. But I'll give you a reason why it's difficult for me, okay? I say the neutron star is like a magnet. I pretended that I understand electromagnetism, and I pretended that I understand this magnetic field, but I don't. In fact, I know how to build magnetic fields. I can build neutron stars on the computer, okay? But all the neutron star magnetic fields that I build explode. Every single model I have is what we call unstable. So they can't be true. And in fact, I believe that is true for every model on the market. So nobody can build on the computer a magnetic neutron star that doesn't explode, or the magnetic field stays the same. Okay? And to me, that is also a big problem. So I'm afraid 50 years, more than 50 years after the discovery of pulsars, we still don't know. And that maybe tells those of you that are young, right? Science is not over next week, right? Some problems are hard. Sometimes you're just waiting for someone brilliant to come around with that idea that we just don't have because we are married to the past, right? And that's just the way it is. You just have to be patient. Find something else to do in the meantime.
If the maximum mass of a neutron star is around 2 solar masses and a black hole can form around 10 solar masses, what exactly happens in between those ranges?
Nice, thank you. So, I think there's nothing stopping a black hole from forming smaller than that, okay? And I think that what happens is where the neutron stars end is where the black holes begin. Now, I'm afraid in this case, the LIGO collaboration has done us a great disservice because in describing the detections, they want to make sure that it's a black hole and not a neutron star. So they invented a gap in between. That doesn't have to be there, okay? Invented, I said it sounds a bit rude, but they classify the data as either black holes or neutron stars, or I don't know. And that got some people thinking there's nothing in that I don't know region. I don't think there's a reason why you can't get black holes there, right? There might be some argument that some matter falls in, there's some little gap, but I don't think so. I think black holes can form smaller. In fact, it could be that they can even overlap with the neutron star mass range if you can find out some weird way of making the neutron star a little bit unstable, even though it could technically be stable. Something that depends on how it collapses, okay? I don't know that. I don't think that's known in detail because it's very difficult to prove, right? This is not an exact science where you have a mathematical proof that this exactly happens, okay? Yeah.
I have a question. I've done some research and I found out that in the core of a neutron star, electrons and protons combine. I don't know how this works.
Aha. Okay.
Because the electron's velocity in atoms, they are stable because the electron's velocity is enough to keep it away from the protons. And the protons electromagnetic can keep the electrons in, I can't say orbit, but...
Okay, see. So, I'm not sure exactly that the protons and electrons combine. They could in principle, okay? Because if you squeeze hard enough, you squeeze them back into a neutron. A neutron is effectively a proton and an electron together, in a sense, right? There are nuclear reactions that create protons and electrons from neutrons and the other way around. That's in fact how a neutron star cools, okay? By combining protons and electrons into neutrons and the other. And these processes go on all the time. So you're kind of on the right track. And in fact, you're so young that I'm afraid that when you get to university age and you start doing your own research, you know, you're going to be way ahead of all of us. That's what scares me now. But I will be old enough to have retired, so for me it's okay. Ajit will be worried. He'll be coming for his job soon, right? Is that your plan?
But if the electron will combine with the proton,
yes,
then it can't exactly be a neutron because the electron's mass is not accounted for. I learned that
that's
protons and
correct.
neutrons have the same mass.
That's correct, but there is a pesky thing you're missing, which is called the neutrino. The neutrino has energy, and according to Einstein, because it has energy, it has mass. And if you put that mass in there, it's exactly what you need to balance the masses. You're right.
So you're saying when they combine, a neutrino is emitted, which
Yes.
takes away some of the mass.
Or when they combine the other way, you need to put in a neutrino. Okay? So neutrinos are the devil in this causes all sorts of havoc. So your calculation is right, but you're just missing a tiny little thing.
Okay. Thank you.
Thank you.
Hello. Thank you, sir, for your beautiful lecture.
You're not going to read out the whole book, right?
Oh, no. What cause of gravitational waves is accelerating mass?
Sorry, what? Good.
What cause gravitational wave is accelerating mass?
Aha. So, in general relativity, whenever masses move and accelerate, you can imagine this, right? Gravity is what we call space-time. It's flexible. So space and time together, everything moves through space, right? Also moves in time because it takes some time to get to places. Space and time are flexible. And what happens is if two stars move around each other like this, the information has to get to you. Okay?
By electromagnetic, no?
No, by changes in space and time, which we call gravitational waves. So as the two stars go around one another, you see the gravitational field changes, right? Because they change position. So gravity changes. And the way that information is propagated is in gravitational waves. And they're like electromagnetic waves, although they're not created by charges, they're created by mass.
Accelerating mass. Yeah. So it's a mechanical or non-mechanical wave?
This is almost, in a sense, they're like, you can think of space and time as being elastic. So like a rubber, okay? And that's more like elastic waves in rubber.
Elastic.
But they're also like electromagnetic waves. So I don't really know if there's a right answer or a wrong answer.
So here is again dual nature of wave, like light is playing a crucial role.
They're very, very similar to light, but they're not light. Okay?
So we have to think.
Hi, over here. Yeah. Thank you for the great lecture. Firstly, it's very hard to give a lecture to such an audience, very diverse audience, so thanks for that. So I have a couple of questions. In one of the slides, you had mentioned that there's a large gap between what happens at the LHC now, that experimental zone, and what happens at neutron stars. So is there any experiment planned for high density, high energy experiments? So that we can sort of bridge the gap and not rely on observations which might not be timely. So that's the first question. And the second question is, for any of the observations that you made in this lecture, is there any need to go beyond the standard model, or does it all fit within the standard model? Is there any need to, say, have a new particle at all?
Okay.
Thank you.
So let me start with the first one. So the diagram I showed, you could fill in a little bit more, because there are experiments that go a little bit more higher density, and we know now that when neutron stars crash together, like in my movie, the temperature goes up a little bit higher than we used to think. So we're a little bit blurring this. There's still a gap, and I think there's probably no chance of anyone ever providing the money that you would need to build a collider experiment that could join the two, okay? But there is an experiment that's coming called FAIR in the US, which will start probing these reactions that come with the Kilonova outflows. Okay, so we're going to learn more about that part of the story. But the neutron star high density physics is probably not going to be probed by colliders, I think. It's probably too expensive. I've not tried to figure out what kind of experiment you would have to build, and I haven't worked out how much it would cost, but I think I don't want to. Or maybe it would be good for this kind of talk and say, we could do this, provided you all chip in, with, all the GDPs of all the countries, we can do this, yay. And then you get just locked up in the loony bin immediately. I think there's no alternative. The other question about standard model, yeah. So I think for neutron stars, we don't really need anything beyond the standard model, although there's quite a lot of work now going on, things like, if you've heard about axions. So axion is a supersymmetric particle that may or may not exist, that people like to play around with, and there are some discussions about what they could do to neutron stars. And for cosmology, when we start measuring with radio pulsar timing perhaps more, if these long gravitational waves are cosmological, then that might tell us if we need to break the standard model, perhaps to explain the expansion of the universe. That's question is way too big for an afternoon, right? I think, but yeah, so it could be.
Hi, thank you for the really great talk. So my question is fairly easy, like in the temperature versus density graph, how do you calculate that phase boundary that you showed?
Okay. So these are calculations in quantum chromodynamics, where you work out, you try to work out everything. But anyone here in school does mathematics, any kind of mathematics, ever done a sum? Okay, come on guys, put your hands up if you've ever done a sum. Okay, now how many of you have ever written down the minus sign in the wrong place? A minus sign in the wrong place. Okay, so the standard model has something called the sign problem, which basically means there's some minus signs combining with plus signs, which means that you can't calculate the thing you need to calculate. And that's basically what sets us back. If we didn't have that, we could calculate in QCD everything. But we can't because of a minus sign that shows up in the wrong place. So some of these are kind of guesswork, some of them build some computer simulations and so on, but it's a pieced together story. And we'd like to know, which is why we do experiments like the LHC. Okay.
Hi. One of the problems with the electromagnetic spectrum astronomy is that when a nova happens, a kilonova or a supernova, we have observations post that event.
Yes.
We don't have observations prior to that event.
Yes.
In the slide that you showed, it looked like that the gravitational waves came first. Now, yes, it is also presumed that neutrinos will also come first prior to have the electromagnetic spectrum.
Okay.
So is it theoretical or is it practically possible to combine a neutrino observatory with a gravitational wave observatory to find data, electromagnetic spectrum prior to a nova happening? Yes. Is that possible?
Okay, so let's unpack this. In principle, yes. Gravitational wave signal will happen before because you have the gradual in-spiral, the kind of thing that LIGO measures routinely now for black holes. And that, for neutron stars, can happen, a minute before the merger, or actually several minutes before the merger, okay? So in principle, you have a warning that these two stars are going to crash together some minutes from now. In which case, you can alert your gamma ray friend to look in the right place, okay? There's going to be a gamma ray burst, there's going to be a kilonova. The kilonova takes, weeks, months. So, yes. The problem is this. First, you need to catch that gravitational wave signal early on. You can't take 6 months to do the data processing. You have to catch it live and be confident that this is going to happen. That's his problem, okay? But that's one of the things that people are working on now for the next generation, 2030s, what we call early warning alerts. So that instead of post-processing, say, now there's a warning, but it's not very precise. We hope that this is going to be much more precise. And also, the other problem is, in gravitational waves, it's really difficult to pinpoint where something happened in the sky, which is why building LIGO India is such a crucial idea, because having the detectors spread out helps with finding the localization in space. And again, of course, if you're going to tell, look, you can't tell an electromagnetic astronomer that something is going to happen somewhere in the sky 10 minutes from now. They're just going to say, excuse me, do you understand the boxes we're looking at, right? So they're just going to tell you to go away. So unless you can make the error box in the sky really small, and that is difficult, as I said, with gravitational waves, clearly we can make it small enough that with post-processing we can convince it. That's where we are today. Where we need to be for your ground vision is something different. Then you said neutrinos. Neutrinos, yes, they will be emitted during that collision. So the first thing that comes out will be neutrinos. But I'm not sure the neutrino astronomy will reach far enough, because we are looking at very distant parts of the universe. And so there might not be much of an overlap. If there is, that would be fantastic. I'll give you an example. If we were lucky and a supernova were to go off in the galaxy, and frankly, we're overdue one, right? If a supernova goes off in the galaxy and LIGO is running and IceCube is running, we would have spectacular data for the dynamics in the neutron star, in the supernova core, okay? Something we couldn't dream of decades ago. But the problem is the gravitational waves are weak. So if we go to other galaxies, we might not see them. So we have to have a supernova in our galaxy, and because they happen something like a few times every century, if I go asking for money to build LIGO to see this supernova, and I say, yeah, it might happen in the next 30, 40, 50 years if we're lucky, I don't think there's going to be much money coming my way. Which is why going to the distant universe, where things happen equally rarely, but there are many galaxies, is important. Okay? And that's so, your plan is great, and I hope it comes off. But we have to do a lot more work before we get there.
So what kind of proofs do we have which says that the neutron degeneration pressure holds the neutron star?
Proof and proof. Well, you can work out that it should be able to do it from the nuclear physics and the gravity, but if you change gravity a little bit, if you change the nuclear physics a little bit, it changes. So this is part of the story. We try to figure out how heavy neutron stars are, how big they are, because if we can make this match with one of these curves for mass and radius, which come from nuclear physics theory, then we can confirm that these theories work. At the moment, we've got too many theories, too many calculations, so none works exactly, and the observations aren't good enough. But we'll get there, or you'll get there, because it might take another decade, 2 decades. So those of you that are young today will see it. Those of us that are, well, you're not old. Those of us that are a little bit older might have to see it from retirement, but that's fine too. Okay.
Sir, exactly my question is about space-time. Okay. As we know, space-time, gravity is not a force, it's a fabric of space and time, curvature of space and time. And what exactly is the space? Because when we compare it with a fabric or a cloth, when we place a mass on it, it bends because weight is acting on it. But when we compare it with the stars or heavy mass objects in the celestial in space, but we can't realize it with the fabrics, because it's very hard to realize. So can you give some like?
It's no. So you've seen, I mean, you've seen out in the planetarium, this bent thing with things, clocks on it, right? So we like to visualize the bending of space and time that way, either through clocks slowing down or space being curved in some way that we can understand. But if you want, you can try, come up on the blackboard and draw 4 dimensions. You can't do it, right? We can draw on 2 dimensions, we can try to do 3 with perspective, right? But we can't draw 4. And unfortunately, we also can't visualize in our brains 4. So what we need is some crutch, and that's where this bend thing comes in. So it's a great illustration, but it's not correct, right? And so the question is, your question is really deep, I think. You're asking, what is it? I don't really know. I don't think Einstein knew. He just figured out that if I calculate like this, and he built it on special relativity where clocks slow down and so on, right? If I build my theory like this, then it looks nice, right? There was a step Einstein took in his calculations where he said, look, this is the easiest theory I can write down that does it this way. It's been over 100 years, right? He was guided by aesthetics, or maybe he couldn't calculate for something more complicated, I don't know, but we're still working with this because it works. So we need to get our head around this. There is a thing called space-time that apparently is bent in some way that we can't sort of visualize, where clocks run slow, okay, fine, which we can't really understand and comprehend, but it works. So hence, because of this problem, that's why there's so many talks and so many things about space. Some people don't like it because it challenges us to understand these things. It's really difficult to understand, and it's difficult for us to explain, right? Because actually we go back to these diagrams and drawings, and they're actually all a little bit wrong. So it's all in the imagination and the calculations. And because the calculations work, and they predict things, they predict gravitational waves, which we discovered, right? They predict black holes, which we discovered, right? The theory predicts light bending, which we discovered. It predicts, you know, the slowing down of clocks in gravitational fields, which we measured. So the theory does a lot of things, right? So the fact that we don't understand the philosophy, the sort of picture, okay, we're working on it, we should work on it. So think about it. And then when you know, go to Ajit and explain to him. Or write to me, I would love to hear it.
Okay, so no one knows what exactly the space-time, and no one knows what is it made of.
It is made of space and time. That's it. But if you ask yourself, what is space? What does that question mean? You know, how do I measure space? I take a ruler, right? But if I take my ruler and Ajit brings his ruler, and I'm living in the UK, you know, sorry, you might be inches as well. Okay, so I live in Germany, so I have to use metric, and I go to the UK where they use inches, they're not going to be the same rulers, right? We don't agree on how much space there is between us two, right? Time is even worse. How do we know that my clock, actually now we all use GPS, so now this joke doesn't work anymore. But you know, in the olden days with clocks, right? How did you know that your clock, grandfather clock, told the same time as the one in the next room? You didn't, right? But they could tick at the same rate, kind of, or did they? So space and time are fundamental mysteries, right? Because we live in space and time. But do we know what they are? I mean, this is real philosophy, right? How does time work? I love those, you know, the physics of time. Why does time move to the future? Why can't I get younger while he gets older? You know, that would be great. Just stay the same, or stay 10 years ago, or something like that. It doesn't work like that. Time runs to the future, but we don't know why. Right? Many ideas? We don't know. So, sorry, I could disappoint you. I don't know. There's probably someone in the online audience shouting, saying, tell him this. Or Ajit is fuming because I'm not telling you the truth, but I don't know.
Thanks. Hi, sir. So you kept on mentioning about gravitational waves, but I couldn't exactly grasp the concept. Like, what exactly does the crest and the trough of that wave, like gravitational wave, signify? And also, like, let's say hypothetically, we were hit by one that but particularly strong enough. So, what exactly would we experience?
Okay. Now you need to come here and give some popular talks on gravitational waves. Okay. So, a gravitational wave is effectively, as I said, it changes in space and time because you accelerate. Basically, it tells you how did gravity change over here because these two stars went around one another. And you know it's changing, right? Because the gravity is different from this to that. Okay? So, Einstein's theory then predicts that gravitational waves stretch and squeeze space and time. Okay? Now, I'm going to simplify this so much that it's criminal, but I'm going to run for it after, okay? You will find me in the car park. Okay? Gravitational waves stretch and squeeze space and time. And so imagine if you stand up like this, it will stretch you like that, and then squeeze you like this, while at the same time stretching like this and squeezing like that, okay? Like this. And then it comes in two flavors that we call polarization. So the other one is rotated a little bit like this. Now, imagine if this was a strong effect. If you were standing close to these colliding black holes, right? You would stretch into a thin spaghetti, right, and then be squeezed together into a thin spaghetti. And you wouldn't like it, right? Now, the reality is that when the waves come here to Earth, they only stretch you by something like, for you, 1 part in 10 to the 21, was that a million? 1,000 million, millions, right? In 1 meter. So you don't feel that very much and you're lucky, right? Now, the LIGO experiment, or LIGO India for that matter, measures this, and you can try to get your head around how they can do that, right? Because 10 to the minus 21 in 1 kilometer is 10 to the minus 18. That's 1,000th the size of the proton and the atom, the nucleus, right? Which ultimately these instruments are built on. So you're detecting something that's 1,000 times smaller than the bits that make up the mirrors in this instrument. Surely they're just making it up. But you can do it because you have many atoms in a mirror and then many photons in the laser light. So the statistics, this is the one time the statistics does something good. Right? It makes it work. Actually, statistics does many wonderful things, but you also know they can prove anything with statistics. So that's a short story, but I think you need a couple of talks on gravitational waves.
Sir, I'm just curious then. You said everything will stretch and squeeze, right? So, like, how do you, with what respect, the LIGO detector detect the like stretching and like shrinking? Like, with what reference do you know it's shrinking, squeezing? When everything is squeezing, shrinking, how you know that it is stretching?
Oh, God, I love that question. That is the best question ever. You always get that question. The question is this, okay? You're measuring how the length changes, right? But the ruler changes as well. So surely that doesn't work. And then what you want is someone to say, oh, I didn't think of that. Take back the Nobel Prize. Come on, they just made it up. Okay. This is a really difficult question because it's not easy to explain the answer. Okay? And I've seen so many answers to this question because it's very common. You say, talk about stretching and squeezing, the ruler must change, it doesn't work. Right? But the reason why the explanation of stretching and squeezing is cheating, I didn't say anything about time. Okay? So the stretching and squeezing also influences time. So one way, in fact, of calculating the gravitational wave response in LIGO is to fix in your calculation the distance and say it is exactly 1 kilometer, and it does stretch and squeeze, but the clocks change, okay? And so that's what saves you. So you have to check the clock. So it's space and time, not just space.
Yeah.
But then you talk about stretching and squeezing, which we understand as this, right?
Yeah, the clock also, like time also varies, right? Like gravitational waves also affect time and space, both affect.
Yes.
Like it will also, like whatever you measure, it will like affect the instrument, right? Like that also shrinks and skews, like stretch. So
as I said, you're right. So it's a calculation when we teach gravitational waves that we usually do in two ways. We usually do it by fixing those arms, calculating the time it takes for light to go, okay? Or we let the arms sit in the middle, we let the arms move. So there are different ways of calculating the same thing, and the answer is the same, right? So it just tells you that you have different choices in the mathematics, but the answer you get in the physics is the same. That's why we believe it. But this is precisely why people had troubles with accepting that gravitational waves would be real, because these kinds of objections and the difficulty in explaining, okay? And it took, from Einstein predicting gravitational waves in 1916, about 50 years until the theorists believed them. And it probably took another 50 years with the LIGO detection that anyone outside the gravity theory community took this seriously, okay? Because of these difficulties. Einstein himself famously wrote a paper when he was a little bit older saying first, gravitational waves don't exist. And then someone talked to him and said, look, you haven't calculated this quite right. So then he wrote a paper saying, gravitational waves do exist. And then he thought that was a bit too brave, so it basically ended up being a paper saying gravitational waves might exist. And that, I think, is a good description of where we were up to the mid-1960s. Okay.
Sir, one more, like how did you get that sound for that footage? Like sound won't travel from space to here.
Oh,
like,
no,
because
that's just cheating.
Okay.
But what you can imagine is there is something vibrating in the detector, and I can take that vibration and run it through a sound synthesizer, and I get the sound. And the frequency is exactly like that. That hasn't been changed.
We could, if you don't mind, you could take some questions from the online audience also.
Oh God, no.
Yeah. One is, what would be the behavior of neutron star if it is in a system with a white dwarf?
Ah, okay. Well, now it's going to be the bully, right? Because it's the dense thing. But eventually, depending a little bit on how close they are, but because white dwarfs are much bigger, neutron stars can be swallowed by white dwarfs and actually fall to the center. So it could be that some of the white dwarfs we see have neutron stars sitting at their centers. And then you can ask, how would I know? So neutron stars and white dwarfs will collide, just like neutron stars. But now the white dwarf is so big that nothing particularly exciting happens. I think the neutron star just falls in. So I don't think there's much work on that. There should be.
There is a slightly more technical question also. How does the pasta structure in neutron star crust be associated with the thermal evolution of the neutron star?
Oh, nice. Okay, so if you remember, I had a slide about 7 states of matter, okay? And then I started talking about 8. Last night I thought, well, I should put one more, 9. But I kind of like the number 7. So I stayed with 7. But there is a 9th state of matter, which is called nuclear pasta. Now I feel a bit hungry. Okay, so it's called nuclear pasta because at the very high dense region of this neutron star crust, that is a solid, the nuclei can form funny shapes. They're not round anymore. Because there are other nuclei close, they can sort of join up and form like spaghetti, or plates that we call lasagna, or other shapes. They're called the nuclear pasta. And so the question is, what does this pasta phase, which could be some 100 meters in a neutron star, have to do with the thermal evolution. And so this is a really technical question, but basically the answer is it could have quite an important effect, because how do you cool something down? You have to move heat around, okay? So it could be that if you put in a preferred direction, so some plates or some spaghetti, that it says it's easier to move along the spaghetti than to move across the spaghetti. It's also easier to eat the spaghetti, but that's a different. So if it's harder to move like that and like that, then the electrons that dictate how heat is moved around could find it easier to move like that, and that could affect the cooling. I think the details for that aren't worked out, but it's a really good problem for people to work on.
Okay, so we will, you have a last, okay.
So I want to pick that last question on a celestial level. Okay, now imagine a neutron star which is not a perfectly round thing. Okay, so it is bulged on one side. Now due to that, it will have its own gravitational waves, right? It will produce its own gravitational waves. And also, a neutron star, it is not perfectly round.
Okay.
Yes. Let's say on a heavier side, it's relatively heavier. Okay.
Yes.
So it will produce the gravitational waves.
Yes.
Now, and also you said
He's
that...
He's looking for them.
Okay. And also you said that 99% chances are like all the neutron stars are pulsars.
Ah, okay.
Wait.
Let's take all neutron stars are not pulsars.
So now, if it is the case, now it is pulsating and also as well as it is producing gravitational waves. So there will be this interference. Now, how would we detect those? How would this pattern change?
Okay. So first is a great question. So we have something called neutron star mountains. The Earth has mountains, right? It's not, if you know these pictures about the Earth's gravitational potential, it's not a sphere. It's dented and stuff. Right? So we're thinking neutron stars could have mountains, like you said. If they spin, this is going to create gravitational waves. Great. So you go and calculate, which I have done with my colleagues and others, how big a neutron star mountain is. Okay? And the answer is, the biggest mountain you can build on a neutron star, we think, is something like 0.1 millimeters high. Okay? Now that sounds small, and it's too small, probably, but actually it's within the region where it could be detected by LIGO now. The problem we have is, this is the biggest mountain, right? What are the actual mountains of neutron stars? Nobody knows. We know what the smallest mountain is. It's got to do with the magnetic field, but I just said earlier, I really don't understand the magnetic field. So I don't know the answer, but I can guess, okay? And that's too small to ever be detected. So somewhere in between, we will never see this till we could see this today, are the neutron star mountains. So this could be, it could be that Ajit is sitting on some secret results from LIGO that he doesn't want to tell us about, but at some point from now to the future, I hope we see this, because it will tell us something that we don't know about neutron stars. Okay? So this is a great question. All neutron stars don't have to be pulsars because the magnetic fields could be too weak. And so as the star gets old, the field gets a little bit weaker, or it starts spinning too slowly to drive this mechanism that I said we don't understand. It's called the pulsar death line. So slow pulsars, we wouldn't see. Although we've learned recently that we might see them after all. So there's surprises in astronomy, which is good. Right?
Okay, the last question from the youngest member of the audience.
So, massive objects bend light.
Yes.
We know that.
Yes,
and
we know
we can also see things only because light reflects off them.
Yes.
So if light, I've seen neutron star images, but if we see a neutron star, well, that means light bounces off the neutron star and comes back. But wouldn't light be hindered when you see it? Because that may not be the actual image, because the neutron star's gravity will interfere with the light.
Okay. You have seen, I know you've seen, the pictures of what black holes look like, right? You've seen these pictures where you can actually see, if you're a disk around the black hole, how you can see it behind because of light bending. right? You've seen those pictures. Now, a neutron star is not quite as strong in bending light as a black hole, but it does bend light, so you can see a little bit of the sort of edges behind the horizon, right? So you're right, the picture that we would see if we could take a picture would not be the actual star, it would be changed because we see a little bit more because of light bending.
So if the light is bending, that means we see beyond the diameter which we would normally see if it were, say, an iron sphere.
That's correct.
So that means what we see will be slightly bigger because that extra, what should I say, circumference will be put on the edges. So what we see is slightly bigger than what it actually is.
That's right.
Okay.
Well done. Now go home and calculate.
I think this is a very good time to stop. I know that you have many more questions, but you can catch Nils with a coffee while you're having coffee. So let me thank all of you on behalf of ICTS for coming, and in particular, let's thank Professor Andersson for this wonderful lecture and answering all these very interesting questions. So.
Thank you.
I also want to remind that this KAAPI with Curiosity series is a monthly event, and there are several interesting talks on very different topics. And if you would like to keep up with our activities, please sign up for getting an email announcement. There are places that you can sign up with an email. We are also on social media. There are social media handles of ICTS, so please subscribe and like and forward and do all kinds of nice things so that we can spread the word. So thank you very much, and I hope to see most of you and your friends in the next event in November. Thank you.